Let's see how this works. Hi. So thanks for joining us. We're going to work on limits today. So limits go like this. And it's not like limits as in I've like had my limit with you, like I've hit my point where I'm going to like crack. It's more like for us in the calculus, we're going to use it as this idea. And I think this is an easy way of talking about it. It's going to be what does it look like? Okay. What does it look like? And when I mean what does it look like, you know what? If I say here's a function f of x is equal to x squared plus 3. What does it look like when x is equal to 3? What does it look like? Well, we have a way of writing that, and we will plug it in. And we say, hey, it looks like 3 squared is 9, 9 plus 3 is 12. It looks like 12. The function f, when I plug in 3, it looks like 12. Right? And if I had graphed this on the graph, 1, 2, 3, that's my vertex. Let me graph it up. When x is 1, 2, 3, the y value, it looks like 12. Okay? So we have ways of doing functions and saying what does it look like. But what if I gave you a problem like this? I say f of x, f of x is equal to, let's do x squared minus 9 over x minus 3. X squared minus 9 over x minus 3. And I ask you this question. What does the graph look like at x equals to 3? What is the graph at x equals to 3? Well, we plug it in. We say, hey, what's f at 3? And we plug it in, 3 squared minus 9 over 3 minus 3. We end up with a little bit of a dilemma. 3 squared is 9, 9 minus 9 over 3 minus 3 is 0 over 0. Now, do you guys remember what happens when we have a 0 over 0? Is that a number? Is that an answer for us? And the term we're going to use for this is called indeterminate. Means because we can't determine what it is. So we're going to try something else. Let me rewrite this problem. Can you guys factor x squared minus 9 over x minus 3? Is this factorable? Now, we talked about this before in our other graphing problems from before. But let's see if it's factorable. It's going to be x plus 3, x minus 3 over x minus 3. And that's what f of x looks like. Okay. And some of you guys might be seeing this already. I see x minus 3 and x minus 3. And if we divide them out, what does that create? Remember, what does that create in our graph? It starts with an h. Some people will use this as a way of showing affection. You have a hole in your head. These are holes. And we say, hey, the hole happens. Let's look at the graph. What does the graph of x plus 3 look like? We have x plus 3 left over. That is y is equal to mx plus b. The slope is 1. The y-intercept is 3. 1, 2, 3, put a dot. Rise over run. Rise over run. 1 over 1. So what does this graph look like when x equals to 1, 2, 3? That looks like, what does it look like if I plug in 3 here? 3 plus 3 is 6. The graph looks like 6. And we call that a hole. The hole happened at 3, 6. So I want to show you guys something. And we've done this before. Let's go to Desmos real quick. Oops. I'm going to go ahead and graph this. X squared minus 9 divided by x minus 3. And we end up with a line. our crazy equation, x squared minus 9 divided by x minus 3, looks like a line. Okay, great. Thank you. It looks like a line. Okay, a line. I'm going to go ahead and do something with this. I'm going to go ahead and bring back our notebook.
Oh.
And, oops, that was wrong. Okay, so our graph kind of looks like the graph that we drew, but we said we have a hole at x equals to 3. Let's zoom in when x is equal to 3. Now when x equals to 3, let's see if we can find that hole. Go take a look. And when x equals to 3, x equals to 3. Oh, do you guys see that? It's undefined, right? And that's, remember we mentioned that's our hole. Now in math, there is no way really for us to say what that hole is until we come up with something called limits. And the limit, we're gonna write it this way. When I say the limit, as x approaches 3 of f of x, or in this case, the limit as x approaches 3 of x squared minus 9 over x minus 3. What does the graph look like when I plug in 3? Now, we showed it back here. Could I really plug in 3? When we tried plugging in 3, did that work for us? Did it work out pretty? When we tried plugging in 3 here, it didn't work out, did it? So in math, my question is, where did I get the whole 6 from? I went ahead back here. Right here. After I crossed out the x minus 3 and x minus 3, we're left with x plus 3. And then we plug in the 3. 3 plus 3 is 6. And the graph looks like it's 6 spaces up. Okay, that's what the hole is. But in actuality, this problem does not exist at 3. If I ask you this question, what is the f of x? What is f at 3? What is f at 3? Do we have an answer? We said there was a hole there, right? The answer is does not exist. It does not exist. Because the value doesn't exist there. There's a hole. Right? Your parents said you better be home at 3 o'clock, and all of a sudden, when they show up, you're not here. There's a hole. You're not there. So we have a way in math to re-describe that. So instead, what we're going to say is, hey, the limit is what should it look like, right? It's not what is it. Remember the word is means equal. My point is not what is it. My point is what should it have looked like? What should you have looked like if you worked really hard? What should it have looked like if you studied for the test? What should it look like, I don't know, if you're paying attention? So I want you guys to look here, and on this graph, on my left, you guys all see my left? What does the graph look like as I get close to 3? I see the y value is 5.9, 5.96, 5.97. So as x gets closer to 3, as x approaches 3, as x gets closer to 3, what does the y value look like? It looks like it should be 6, right? But do you see how all of a sudden dies? And that's what limits allow me to say, what should it have looked like? This answer should have looked like 6. Now, we're going to do this a couple of different ways. We're going to do the easy algebra one way, and then we'll do it like the algebra 2 way. But both of these ways will give us pretty much the same answer. So what does it look like? Let's come up with a table. The table is going to be numbers that are close to 3. And we're going to say this is going to be 3.01, 3.1. Okay? Now, just to say this on a number line, if this is 3, 3.01 is really close to 3, and 3.1 is farther away. Right? Think about money. I have $3.01 and $3.10. On the left side, I'm going to put 2.99 and 2.9. Which is closer to 3? 2.99 is, right? 2.99 is right next to 3, and 2.9, which is like $2.90, which is farther away. So as we get closer to 3, we're going to see what does that y value become. The reason why I chose 3.01 and 3.1 are numbers that are getting closer to 3. So this is my goal, right? And as I get closer, 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 if I'm getting closer on the number line, I would first hit 3.1, and then I would hit 3.01, and then I would finally be at 3, getting closer to it. Okay, so on my calculator, I'm going to switch over to a calculator now. And this is kind of a terrible calculator. We'll use this one here. But if I write parentheses, no, adds. If I take the problem and I say, hey, x squared minus 9, which is going to be 3 point, let's do 2.9 first. Sorry. 2.9 squared minus 9, and we're going to divide that by parentheses 2.9 minus 3. My answer is 5.9. Let's write 5.9 in. 5.9. Okay, we're gonna keep on going, and you could follow along. Yep. Okay, let's do the next one. 2.99. 2.99 squared. We're minus this from 9 equals. And again, we're plugging this into this equation here. We're plugging this into this equation here. Right here, we're plugging into that equation. We're saying, what does it look like at x squared minus 9 over x minus 3? And we're divide this by parentheses 2.99 minus 3. Hey, this is 5.99. Are we closer to 6? Yeah. On the right side, let's try the one over here. Let's start at 3.01. 3.1 squared minus 9 divided by parentheses 3.1 minus 3. And that's 6.1. Okay, which is kind of close to 6. And if we get closer, 3.01, 3.01 squared minus 9 divided by 3.01 minus 3. 6.01. So one of the important things about limits, if I'm looking at a point on the graph, not infinity, okay? Not infinity, but any point on the graph, let's say I'm looking at 3. The left side looks like what? 5.9, 5.99, probably 5.999, 5.99999999999999999. All those numbers are getting closer to what? 6. And a way to describe limits is that it's not what is it. We said if I tried plugging in the number 3, when we tried it over here, if I tried plugging in 3, we got no answer. That's meaningless to me, right? I don't know. Right? Have your parents will ask yourself like, hey, oh no, I'm sorry, that's not the way. Dang it. Your parents will ask you a question, and you, of course, automatically answer, I don't know. What are you talking about? But could you just give them like a guess? Right? Hey, when's your dad gonna be home? I don't know. I don't know. Why do you ask me? Well, you could say he comes home usually around 6. So this is what we're gonna do. The answer that we tried plugging in does not exist. But what does it look like? It looks like 6. And that's what a limit is. A limit says, I don't care what it is, I care about what it looks like. Now, let me give you a different graph here, just to talk about that, illustrate that real quick. And then we'll talk about, in essence, like a little story. If I give you a graph, what's going on here? You are killing me. Okay, we give it as a graph, and the graph is called f of x. This graph is called f of x, and this is what the graph looks like. Oh, this is 4, and this on it. No, I need to close it and then try again. Okay, this is the number 3, and I'm gonna do something kind of weird. Call that 5. Okay, so if we ask this questions. What is 1? What is f at 4? What is the actual value for f at 4? Answer is, and you want to type that into the chat real quick? What is the graph going to be at 4? What does the graph look like? What's the y value at 4? Is it 3? Or is it 4? Or is it 5? Okay, I'm hearing 3, I'm hearing 5. So which of these values actually means it's actually there? Does the hole here mean it's touching or not touching? How about this? It is 5, and others are saying that now. It's 5. It's filled, yeah, the filled value. That's 5, okay? Well, what if I wanted to say, hey, I get it, it's 5. We all know it's 5. I see it's 5, yeah, duh, it's 5. But how could I represent the answer 3? And that's where limits come in. If I write, oh my goodness, the limit as x approaches 4. What does graph, that's an arrow. What does the graph look like as we approach 4 of the function? Okay, as x goes floating in there, as we say 3.99, 3.999, 4.01, 4.0001. What number are we getting closer to on the y value? That's 3. And that's what limits allow me to do. We're not talking about the whole anymore. We're talking about what does a graph look like it should have been. Okay? Some of you guys will come back to me during grading and you'll say, Mr. Coates, I had an 89%. Can you just round that up to a 90%? Right, that's what it looks like. Doesn't 89 look like a 90? Well, and I'll say, well, that's not what you got. That does not exist. So the idea of a limit is, what should it look like? As we got closer to 4, what should the y value have been? It should have been 3. Now, here's a story on the side. The story is about 3 blind monks. And they're blind, so they can't see anything, okay? So understand, that's what blind means. And they're brought to describe an elephant. And we all know what elephants look like. We all have eyes. We've seen elephants. We've seen them at the zoo. Big ears, right? Thick legs, a runny nose, and a really ugly tail. So the 3 monks go ahead and start to describe this elephant with their hands. So one person grabs on to a piece of elephant and says, this elephant feels like a rope. The elephant must be a rope. The second monk says, this elephant feels like a tree. It's super thick. And the third monk says that, no, you guys are all wrong. This elephant is more like a garden hose. See how wet it is? So can any of these people really tell you what an elephant looks like? And answer is no. They absolutely describe the wrong situation. And when does a limit not exist? Let's give you the idea now. Okay, and a limit, when does the limit not exist? we're going to use this story here, that if I ask you this question, follow-up question, here is the graph of g of x. Okay. Here is, we'll say this is 5 now. Call this 1, 2, and 3. So if I looked at my table, and let's do the table again one more time. This is 5, 5.01, 4.99. Okay. As we approach from the right side, this is what we call the right. We call this the left. As we approach from the right side, what do you think the people on the right say? Imagine if I had two groups, two classes, right? And I say, this is one group of kids, and this is another group of kids. Let me go ahead and draw a different color. Let me erase this and draw some blue kids. Okay. As these kids are approaching their hills, the blue kids will yell, awesome, hey, so what's the value you're reaching, blue kids, the right side? And they'll say, oh, as we march up this hill, we're getting higher and higher and higher, and we are reaching 3. On the left side, I'll ask, hey, the red kids, what are you guys approaching as you guys are climbing up this hill? And they'll say 2. Do these numbers agree? 2.99, and this will be like 1.99. Are these numbers approaching the same number? Is it the same number? They're not, right? So it turns out if they do not agree, here's what we're going to say. The limit as x approaches 5 of g of x, because this is a different graph, right? This is g now. Can we say that they agree? Can you tell me, just like those monks, can they come to a consensus what they believe? The answer is no. There does not exist. The limit does not exist. There is no limit. And that's how we actually describe it. This is no limit. Let me write that a lot nicer for you guys. This is no limit. It does not exist, and we describe that in math terms as no limit. No limit. L-I-M-I-T. Okay. Okay. So let's take a look at another quick example here. So if I give you guys a quick limit example, draw a graph. 1, 2, right? 1, 2, 3, 4. Call that 4. We'll call this number 6. And I'm going to ask you 2 questions here. Okay, that's my graph. And my question is, oh, one more point. What's the limit? And we'll call this f of x. So what's the limit at x? X is numbers. Okay, that's x value. X approaches 6 of f of x of the graph given. Go ahead and give me a response. Okay. 2, I'm hearing 2 from Ramiro. Anyone else? Just give me one more person. 4, perhaps? Oh, maybe. So go back to the statement. What does the limit mean is what should it look like? If I was walking on a trail, if I was just walking up this canyon, Mr. Cody here, walking up the hill, and as I got closer and closer to 6, right? As I got closer to 6, what's the y value looking like it's going to be? If I was coming down the hill, I was rolling over, head over hills, I was rolling, going downhill, and as I got closer to x is 6, what's the y value going to be? Does it look like 4? So the answer is, well, let me give you this idea. What is the actual value of 6? What is the actual y value at 6? The actual y value is 4. That is the actual value. And the limits allow us to say, hey, I don't care about the actual value. I care about the what should it have looked like. Well, this looks like, I'm calling it as 2. That's what it looks like. It looks like 2. Right? A very simple idea now. So looking at a graph is great because I can tell you what that looks like. Now, what if I ask you a dumb question here? What if I ask you, hey, what's the limit as x approaches 0 of the function? Here's 0. What does that y value look like? Looks like 1, right? Good. Looks like 1. And that's what it is. Limits just tell you what a value is supposed to be. The only time it gets a little fishy is when that value isn't the same as what the actual value is supposed to be. Like if you look at x is 6 here, you know what? It's actually 4, but the graph doesn't make you believe that. It's a little deceptive that way. So limits allow me to say, what should it have been? So let's give you guys another quick problem. And that's a problem that you guys will see in the homework. In the homework, it will say, example, f of x is equal to, I'm going to factor this for you, x plus 5, x minus 3 over x plus 5. Okay? Now my question is, what is the limit as x approaches negative 5 of f of x? Right? That's f of x. So I could rewrite it if you want as one big function. I could rewrite this as limit as x approaches negative 5 of x plus 5, x minus 3 over x plus 5. Now, here is the problem. If I plug in negative 5 into the problem, if I plug in negative 5 into the problem, we end up with 0 and 0, don't we? And 0 times anything is 0. So we know that it's not going to work there. We know that there's a hole. Some of you guys have realized that. That's a hole. It's going to be a hole here. So what you always first do is reduce, like we did when we found holes. Reduce the problem. We're left with the limit as x approaches negative 5 of x minus 3. And now we can plug in. And we're left with negative 5 minus 3 is negative 8. And good job, Ramiro. Oh, sorry, good job, Andrew. And that's really what limit is. It's as simple as algebra 2, reducing and then replugging it back in. Now here are the process. This is the process for always finding a limit. Just basic limits. First thing, go ahead and try plugging it in. Go ahead and plug it in, see what happens. You don't know anything about this graph. You can't judge me. You don't know anything about me. So go ahead and plug it in and see what happens. If I plug it in and we end up dividing by 0 over 0, try something else. Why did I use negative 5? Look here. I said as x gets closer to negative 5. I gave you the variable x has to be. So as x is approaching, that arrow means approaching, getting closer to negative 5. What does the graph look like? As x gets closer to the negative 5, what does your y value look like? And the y value, when I plugged it in here, doesn't exist. It's crapped out. So instead what we do is we go ahead and we realize, hey, there's a hole there. So that's reduce the problem and then try again. Ask the girl out, she'll turn you down. Try something else, get a haircut, and try again. And if she says no, just leave her alone. Now you're just stalking her. Darn it, this is being recorded. Okay. Yeah. All right, moving on. So if we're going to follow this idea of what should it look like, well, let me ask you this question here. What should it look like? Now we have other types of limits. We have what we call directional limits. Now limits say what does it look like. So I'm going to ask you this question. What is the limit as x approaches infinity? Oh my gosh, let's go infinity. Of this graph here. X squared over x. No, that's not that one. Let's do an easy one. Let's do 1 over x. Yeah, that's easy. We remember what 1 over x graph looks like? As x gets bigger, x becomes 2, 3, 4, 5. Number gets smaller. And this is what the graph looks like. Okay, so remember this graph here for 1 over x? So what does the graph look like when x goes to infinity? Okay, so you need to conceptually understand this. What does x goes to infinity mean? When x, these are your x values here, as x starts walking itself to infinity, as it starts walking into the desert, what does the y value become? Okay, sorry about that. So as we go to infinity, as x gets closer to infinity, x is going to infinity. Positive infinity or negative infinity. In this case, without a minus sign, this is plus infinity. So as x goes to plus infinity, what does the y value become? What does the y value become? Nope, nice try. So remember this value graph? This graph gets closer to, as x gets bigger, yeah, the answer becomes get closer to 0. And here's a trick that we have for this. We have a way of describing how end behavior of a graph happens for rational functions. So when it comes to rational functions, it's, remember the exponents, is the top exponent bigger or the bottom exponent bigger? In this case, the bottom, so we go to 0. So automatically, without any work, I don't have to draw this. When I'm doing problems like this, you don't have to draw it. You can just ask yourself, what is the horizontal asymptote? Remember, it's the horizontal asymptote. Let's do the same problem. Limit, as x gets closer to infinity, of x squared over 3x squared plus 1. Can anyone tell me what this graph will look like at infinity? What's the horizontal asymptote for this graph? Go ahead and type it in the chat. I'm hearing 1/3. If you remember, if the exponents are the same, we copy the front values. In this case, it's going to be 1 over 3. Now, just to prove this to you, I'm going to plug in a large number like infinity. No, like 100. No, let's do 10. Let's do 10. If I plug in 10, that becomes 100 over 300 and, 301. Isn't this approximately 1/3? If this becomes 1,000, it'd be like 1,000 over 3,001. Is that even closer to 1/3? So as you approach infinity, as x gets bigger, this problem gets closer and closer to 1/3. That was 3. And it's our horizontal asymptote. And when you guys are working on the worksheet today, you'll see that some of these problems are super easy, and I give you the hint. It's just the horizontal asymptote. Okay. So on your worksheet today, you'll be practicing 2 types. One is you'll be factoring. Well, first, if you plug it in, and if it doesn't work, you plug it in and it doesn't work, then go ahead and try to factor. If it's 0 over 0, you know something is factorable. Then try again. It doesn't apply to all of them. No, as we go to infinity, it doesn't apply to all of them. In this case, since we have a rule for horizontal asymptote, yes, we can use our horizontal asymptote rule. But what if I write this wrong? The limit as x approaches infinity of x cubed over x squared plus 1. Does this have a horizontal asymptote? The top is bigger than the bottom. Top is bigger than the bottom. Okay, so we had a rule that if the top is bigger, we don't have horizontal asymptote. So it's going to go, that's right, Andrew, it's going to go to plus infinity. Because if I plug in values, the top is bigger, and this answer is going to be overall positive, so it's going to shoot up to positive infinity. And the answer is infinity. Right? You can say positive infinity, that might be a little better. But it's always positive unless we write negative. So 2 things that we're going to take away just as we start limits is like, how do I find the value limits? One is we could go ahead and we can say, I could plug in numbers here. You can do this table. You guys really want to do this table here? That'll work. Do it from the left side and the right side and see if they agree. You could graph. That would work too. Look at the graph. What does it look like? But I think one of the easiest ways is that first you should go ahead and plug it in. Go ahead and plug it in. If it fails and it's 0 over 0, it's going to be a factoring problem. And go ahead and factor it and then replug it back in. And then try again. That's one of our ways of solving for limits. And our second way is looking at, as we go to infinity, looking at horizontal asymptotes. And if it's not a rule for horizontal asymptotes, maybe if there's no horizontal asymptote, is it going to go to positive infinity or negative infinity? Okay, so that's going to be your work for today. We have a couple more rules about limits, and we'll go over them later as we go through the week. This is our last section, closing off the year. So hopefully this was helpful.